Ethiopian Educational Information and Communication Technology presents Educational Satellite Television Programs.
Hello, teacher. Hello, students. Welcome to today's lesson on freezing point depression. In our last lesson, we learned about the change in boiling point that occurs in a solution when certain solutes are added. We also learned how to calculate the boiling point of a solvent after certain solutes have been added. In today's lesson, we will explain the change in the freezing point of a solvent when a certain amount of solute is added. We will also calculate the freezing point of a solvent after a certain amount of solute is added. Let us begin. When solutions begin to freeze, the component in those solutions that crystallizes out first is almost pure. Let us discuss an example. If a solution of salt water freezes, pure ice will crystallize out of the solution. The solute particles, which are the salt particles, do not fit into the crystal lattice of the frozen solvent, which is the water. This is because the solute particles have a different shape and size. Instead, they tend to concentrate in the remaining liquid. In doing this, the solute particles interfere with the freezing process by blocking solvent particles from reaching a lattice site. Since the solute particles interfere with the solvent particles, saltwater solutions take longer to freeze than pure water. In fact, the greater the concentration of the solution, the greater the interference will be between the particles. This causes the solution to have a lower freezing point. The freezing point depression is defined as the freezing point of the pure solvent minus the freezing point of the solution. The freezing point depression of solutions of non-electrolytes is equal to the molality of the solution times a proportionality constant. This constant is the molal freezing point depression constant, Kf of the solvent. Students, let us do an activity. Please explain why a solution of water and sugar would have a lower freezing point than pure water.
Students, let's get ready. Begin. Time's up! Let's get back to our lesson.
Welcome back, students. When subjected to freezing temperatures, the pure water in a sugar-water solution begins to crystallize on its own. However, the sugar particles slow down the process by concentrating in the remaining solute, thus blocking the water molecules from reaching a crystal lattice site. Pure water on its own contains no solute particles to prevent it from freezing. Was that your answer, students? If so, great job. The freezing point of water is around 0 degrees Celsius, whereas the freezing point of a solution that is 3 parts water, 1 part sugar, freezes at around -3 degrees Celsius. Let us continue with our lesson by learning how to determine the freezing point depression of a solution. The freezing point of pure camphor is 179.0 degrees Celsius, and the molal freezing point depression constant of camphor is 39.70 degrees Celsius, kilograms per mole. We will determine the freezing point depression of a solution that contains 1.50 grams of a compound of molecular mass 125, dissolved in 35 grams of camphor. To begin, we will determine the number of moles in the solute. I'm sure you remember that in order to do this, we must divide the mass of the compound by its molecular mass. Therefore, 1.5 grams divided by 125 equals 0.012 moles. We can then use the number of moles to determine the molality of the compound. To do this, we divide 0.012 moles by 0.035 kilograms. This gives us a molality of 0.343 moles per kilogram. We can use the molality of the solution in the equation we learned earlier in this lesson to determine the freezing point depression of the solution. The freezing point depression constant multiplied by the molality of the solution equals the freezing point depression, which is 13.6 degrees Celsius. Finally, we subtract the freezing point depression from the freezing point of the pure solvent, which gives us the freezing point of the solution. 179.0 degrees Celsius minus 13.6 degrees Celsius gives us the answer 165.4 degrees Celsius. Students, now that we have done this example together, you are ready to try an activity on your own. Calculate the freezing point of a solution of 5.00 grams of diphenyl and 7.50 grams of naphthalene dissolved in 200.0 grams of benzene. Benzene has a freezing point of 5.5 degrees Celsius.
Students, let's get ready. Begin. Time's up. Let's get back to our lesson.
Hello again, students. Did you find this question to be difficult? Let us go through it together. First, you have to determine the number of moles in each solute and then add them together. Then you can determine the molality of the solution. From this, you can calculate the freezing point depression, which is 2.33 degrees Celsius. The freezing point of our solute, benzene, minus the freezing point depression equals the freezing point of our solution. The answer is 3.17 degrees Celsius. In today's lesson, we learned about the change in freezing point of a solvent when a certain amount of solute is added. We also learned how to calculate the freezing point of a solvent after a certain amount of solute is added. This brings us to the end of our lesson. Until next time, thank you, teacher. Thank you, students.